that's my cue to get started. Good morning, everyone. Welcome to NDC Oslo Day 2. It's not a beautiful day outside, but inside it's going to be awesome. We have a lot of great talks here, and I'm really excited to talk about OAuth security here. If you're in the audience, for the record, I cannot see you because there's like 2 bright lights in my face, so I can see like 3 people. But I know that the rest is there, up high in the room somewhere. So yeah, I hope you are going to enjoy this talk. It's kind of an experience for me, always here in Oslo Spectrum, because of the hanging stages. We're basically hanging over the expo floor here, and it's feeling like a boat. So whenever you walk, it like moves with you. So it's absolutely fun to do that as a speaker. So I'll do my best to not get distracted by that, and we'll talk about OAuth security. All right. So if you're here, I'm kind of assuming you're familiar with OAuth 2.0, OAuth best practices and so on. If you're not, this is going to be an absolutely crazy ride because we're going to start from 0 to 100 in like 2 seconds, and then we'll dive deeper into the details here. But if you're familiar with OAuth, or if you're vaguely familiar, I have some really quick introduction coming up in a bit that will help you move around. And then we're going to talk about advanced security. Supercharging OAuth security is the title. So we'll be talking about advanced security measures, things you can do to beef up the security of your OAuth architecture, your deployments, and so on and so on. And the reason we're going to talk about that is because over time, OAuth has evolved, right? Over time, OAuth has seen a lot more usage in practice, which has seen usage in like security critical areas like financial applications, eHealth applications, and that has led to the realization that some of these things are not as good as they should be. And that has resulted in new specs being created, augmenting the security of OAuth. These are not core specs, as in, if you're doing OAuth, you don't have to do these things, but very often it's highly recommended to do these things in practice to ensure that you have a solid architecture. All right? Before we dive in, let's talk very briefly about the OAuth authorization code flow. This authorization code flow is how the interaction happens between the user and an application, and of course your authorization service, server, and so on. And that's kind of the backbone of OAuth these days. This is the de facto standard for user-based flows. It's the authorization code flow with PXE, a security measure, of course, that we're not really going to dive into too much detail. How does that flow work? Well, from a very high level, the user, we have a front channel interaction where the user is using a browser to contact a client application, which in my example is the backend. The backend here is a client-side, or not a client-side, a client application fulfilling the role of the client in OAuth. It runs somewhere on a server-side application, and it wants to interact with that authorization server, the security token service at the top. That's the front channel. And then that's one part of the flow. The second part of the flow is the back channel, where there's like server-to-server communication, where the client application is talking to the STS directly. And that's in a nutshell what this looks like. There's a third leg that we'll talk about at the end of the presentation, and that's basically where we access resources with an access token. Typically, that's going to be API endpoints with access tokens and so on. Now, this is super high level. If you've ever seen the details of a flow explaining this in 3 arrows, it's bullcrap, as in you're not even going to cover a tiny fraction of the details. So I have a slide with more arrows, if that's going to make you happy or not. I'm going to leave that in the middle here, but we'll cover a little bit more detail because we'll need it throughout this presentation, all right? I am skipping on a whole bunch of details in the interest of time and complexity and so on, such as PXE, proof key for code exchange. It is a best practice. I've not drawn it on the slides, but just assume we are using it in practice. So what's going to happen is that with OAuth, the user is basically wants to allow a client to access a resource, an API, on their behalf. So that's going to be the intent of the flow, and that's a request from a browser to the client application running on a server, and that's a signal like, okay, let's start an OAuth flow. Let's run an OAuth flow with an authorization request, which will redirect the user's browser to that security token service. That's essentially how the flow works. That security token service will have to authenticate users. Sometimes there's an active session, so we can skip that part, but the first time, the user will have to authenticate with their account at the authorization server at the STS. So in this case, that's going to be Philippe, my username, and my password is my very fictional dog, Fluffy. So FluffyDog17, and of course we add an exclamation mark for security reasons to make sure our password is highly secure. This is not my real, don't worry, this is not my real password. I'm not that crazy. So please don't try it on my accounts. It's not going to work. Promise. When that has happened, this is not part of OAuth, by the way, 4 and 5. That's kind of out of scope. But if this step is completed, we're going to return an authorization code back to the client. And this happens through the front channel, so there's going to be a response from the security token service that will take the browser back to that client application running on a server. There's going to be parameters in the URL, and one of the parameters is the authorization code. All right, so on the back end, we now have code doing like request.getParameter code, and that authorization code is a temporary artifact. It is basically meaningless to the client application. Doesn't mean anything, can't really use that for anything except one thing, and that's exchanging that code for tokens. Hence the name of the flow, authorization code flow. So the client application goes back to the security token service, server-to-server request to exchange the code for tokens involving things like client authentication and so on. STS will verify that authorization code, sees that, oh yeah, I gave that to Philippe like 3 seconds ago, makes perfect sense, awesome, here we go. And it will return a set of tokens, an access token with the authority to access the API, probably a refresh token as well, and maybe an identity token if you're also doing OpenID Connect. The access token is essentially what we're after in this use case. So with the access token, we can now call the API and achieve our actual use case. That's essentially the setup of the authorization code flow. I have some details of that as well with monospace fonts to make you very happy as developers. So what we basically have here is that authorization request, step 2 and 3, with all of the flow configuration parameters in there. All right, I'm not going to talk about what these all mean. I've added some text if you want to review the slides later on. But that's essentially how this works in practice. And this is probably the world's shortest introduction to the authorization code flow that you have seen, but it's enough for what we need in this session. All right, just one more thing. I'm using some specific terminology here. That's because I teach a lot of courses on OAuth and OIDC, and if you talk about OpenID Connect, you should talk about end users and relying parties and identity providers and so on. And if you talk about OAuth, it's like a whole different set of terminology, and it gets very confusing after a while. So what I choose to do is I use the terms for the use cases that we see most often, right? Most often we're dealing with users who want a client to access an API and so on. So I'm using those terms. So whenever you see that, that's what they mean in the specs in practice. All right, and then our authorization server or identity provider becomes a security token service because it's a security service issuing tokens. So it's kind of a very logical name if you ask me. All right? That was the introduction part. Who am I? I'm Philippe De Ryck. I'm a security expert, and I did a PhD in client-side web security like a long time ago, more than a decade ago. And since then, I've been helping developers understand security. That's basically what I do. I do that through my company called Pragmatic Web Security, through conference talks like this one, through workshops, like the workshop I did at NDC Oslo here earlier this week, or in-house training, as some of you have had the experience, and so on. I also have online courses and basically everything you need to help you understand security. If you're really stuck with some problems that are too hard to solve or too broad or too specific to solve in like a conference talk or a workshop, I also do specific consulting, helping people find the right approach, find a way to solve their requirements and so on. So that's essentially how I stay current and up to date, and how I am sure that what I'm talking about in talks actually works in practice as well. Because there's often a very big disconnect between this is how it's supposed to work and that's the reality in practice. Good. I'm also a Google developer expert. Recognition by Google for the work I've been doing. It's an invite-only program. I don't work for Google. It's just kind of an outreach program. It's really awesome to be a part of that community. And I organize SecOpDev in Belgium. It's a week-long course on application security where we bring in speakers from all over the world to teach about AppSec. All right? It runs in the first week of June, which is like in a week and a half. So you can imagine I'm fairly busy with handling the final details there. But if you want a good reason to visit Belgium in the next 2 weeks, SecOpDev might be the way to get you there to learn about AppSec and experience Belgium. All right? With that, I want to wrap up the introduction here. If you want to connect with me, I'm very easy to find on LinkedIn or Mastodon or Blue Sky or whatever, not on Twitter anymore, so screw that. But in essence, that's where you can find me. I also have a website with the talk slides on there and so on, and a lot of useful resources as well. All right, so grab a copy of that link or just Google my name and you'll find me easy enough to grab some useful content. Good. All right, 9 minutes in, that's a good start. So we have 51 more minutes to cram through a whole bunch of OAuth security features. And I want to start with the first one, and that is by looking at the power of access tokens. All right, so what happens typically in an OAuth deployment is on slides, you always have this very nice scenario. You have one client and one API, and they use an access token. It's like, yeah, that kind of makes sense. And then you start building this, and in reality, you end up with a client accessing multiple APIs, right? Because you have multiple services or multiple APIs and so on. And of course, you can use an access token for that. It's very easy. You have an access token, you throw it at one or API 1, 2, or 3, and they can evaluate that access token one way or another, make an authorization decision, and decide how to handle that. Now, the problem with that is that the access token you're using for this request is super powerful because it gives access to a multitude of APIs, and that also means if that access token is ever abused, that the abuser has a lot of power thanks to the authority of the access token. And that's something we can actually address. So what basically happens here is that the access token will have a whole bunch of scopes, right? In this example, I'm going to use a restaurant review application as the training app, as the example application. We have a restaurants API, we have a reviews API, and the access token gives access to both the APIs, all right? Means if an attacker obtains an access token like this, they know like, oh yeah, I can go here, and I can go there, and I can do this and that, and it basically the access token announces all of those features, especially if it's a JSON web token. That stuff is just encoded in the token, easy to obtain. Second thing is, an attacker can steal that from the client, but we also send it to APIs. So if one of these APIs turns malicious, nothing prevents them from turning around and using our access token to call the other APIs in a malicious fashion. That's also a potential problem that we have with this use case. And then the second, or the third, or the whatever, I lost count here. The other thing is that sometimes you want to have like more secure tokens, as in you want to encrypt them. There's an option where you can encrypt your access token, so it's still a self-contained JSON web token, but the token itself is not readable to anyone except the API with the right key. And to do that, we need a private key to decrypt tokens on the API. And in a scenario like this, we have 3 APIs that can all accept the access token, so they would all need the same private key for all 3, and that's not really how private keys are supposed to work. When a secret is shared, it's no longer a secret, it's kind of a shared value, and you hope it's kind of secure, but this kind of loses the benefits of doing so. And all of these small details, they're not like major issues, but they're things like, yeah, slightly uncomfortable, and that has sparked the development of a new feature called resource indicator. Well, new. A recently added feature, I should say, called resource indicators. It's been around for like 5+ years now, which is not new, but recent in terms of OAuth. And resource indicators allows us to reduce the authority of an access token to a single resource, a single API. And that's essentially what this spec brings to the table. So how does that work? Well, it adds a few tiny changes into the OAuth flow to make this possible. And change number 1 is basically where we have that request starting the flow with all of the parameters in there. Well, in this request, we can now add more parameters. We can extend the request, make it even longer, and we can add something that's called the resource parameter. And that's basically the client signaling to the STS up front, like, hey man, I would like to access the reviews and the restaurants API, please. And the STS can evaluate that. If there's consent, they can prompt the user like, hey, this is about to happen. Is this something you want? Yes or no? And so on and so on. That's step number 1. So we signal up front which resources we like to access. All right? Second change is when we request an access token by exchanging the authorization code or the refresh token later on, we specify a target resource. We specify a resource for which we would like to have an access token. So now this is request number 8 on the slides. We send a request to the STS, we exchange the authorization code or the refresh token for an access token, and we tell it like, hey, when you create this access token, it should be limited to the reviews API in practice. All right, and now we have an access token scoped to one particular audience. That's essentially how this works in practice. What does that mean? This means that inside the access token, you will now find an audience claim, the AUD claim, and the audience specifies the target audience for which this token is valid. So this means that on the API side of things, you can now restrict the audience, which is something that was like sometimes available in OAuth, sometimes it isn't. Now it's very well defined. You can now configure the API to require this particular audience for this particular API in the access token and reject everything else. And that's essentially what this brings to the table. Additionally, the STS does something we call downscoping. And downscoping basically means that instead of including all the scopes for this access token, or for the APIs that the client can access, we only include the relevant scopes for this particular API. And that means that this token is now less powerful than what we had before. Of course, it also means that the client now, the client application, has to handle multiple access tokens, one per resource it would like to access. So in our example from before, we had 3 APIs. The client will now have 3 access tokens, one per API, and handle them that way. And that means that if the token is ever exposed, it is less powerful. It can only be abused against one API. It also means that an API can no longer turn around and call other APIs with the access token it just received, because that will no longer be accepted. And finally, it also means if you want to encrypt your access tokens, you can now encrypt them on a per API basis, where every API has their own private key to decrypt their specific access token. In a nutshell, it handles all of these uncomfortable details and makes things better in scenarios where this might be highly relevant for your use case. All right? We already talked about this, but I haven't shown an image here. I'm not going to show that image because it's basically the same as before, except for exchanging a refresh token for access tokens. So what the client now does is it exchanges the authorization code for access token 1, and then uses the refresh token from that response to obtain access token 2 and access token 3, and now it can call API 1, 2, and 3 as well, and we are done. Good. Takeaway number 1, use resource indicators. It's a recent spec. It is fairly well supported across authorization servers, but it's something that's not used that often in practice, and it's something that might be beneficial for what you're working on. Maybe it is, maybe it isn't, depends a bit on your specific use case. But if it is, if you're dealing with large and complex architectures, if you're dealing with APIs controlled by multiple teams where you not really have full implicit trust between the different APIs, this might be a very useful feature in practice. All right, 1 down, I don't know, 3 to go, I think, maybe 4, depends a bit on how you divide topics, so let's continue this journey. Let's talk about the authorization request, right? Let's talk about this request with all of these parameters that is basically going through the front channel. The front channel is a part which involves the browser of the user. And whenever we talk about front channels in OAuth, we talk about the untrusted front channel, because all kinds of crap can go wrong in the browser, either by mistake or on purpose, by a malicious actor, and so on. So one of the attacks that we see is users, malicious users, attackers, tampering with these parameters. Like, yeah, what if you send this authorization code not to this particular URI on line 5, but maybe send it to evil.com/something something. That's a very extreme example, but you can imagine there's a whole bunch of things that the attacker or a malicious user can tamper with, and that compromises the integrity of the flow. And this is something that has been kind of a problem for a very long time, and something that we always just accepted as like, yeah, it is what it is. We always focus on protecting the other stuff, like the authorization code must be secure and so on, but the start of the flow, the authorization request has gone like unprotected for a long time, and that has changed as well. All right, some of these attacks are very well known and very well documented in the OAuth security best practices. All right, so there's a spec, the OAuth security best practices, that highlights some of these attacks against the authorization request, such as tampering with the redirect URIs in an attempt to steal authorization codes. That's a very realistic attack in practice, or tampering with the PXE parameters to do like a PXE downgrade attack is also a well-documented attack pattern. All right, there's actually a use or an example of a vulnerability like this happening in Keycloak from a couple of years ago, I think 2 years ago. They had a vulnerability that would allow an attacker which tampers with the redirect URI to obtain authorization codes and so on, which can lead to further attacks. So these are not fictional problems. These happen in practice. All right? So what do we do to solve that? There's 2 ways to solve that. The first way is to use jar. And jar is not the Java archive utility. It's basically a JOT-secured authorization request. And the reason I'm saying that is because if you Google for jar spec, you'll end up with the Java stuff, so you have to add like OAuth to your search, and then you'll find the right spec in practice. And jar is RFC 9101, if you like RFC numbers, and it basically describes a way for the client to protect the integrity of this request with all the parameters by putting all of that stuff inside a JSON Web Token, and then send it to the STS. That's in a nutshell what it is. It's fairly simple, fairly straightforward, and I want to show you how that works in practice. All right? So on a slide, what do we change? We add a few things. The stuff in green has changed compared to a normal authorization code flow. First thing we do is we add a new step, number 2. We basically add the generation of a JSON Web Token. right? This is the client starting a flow. It's like, yeah, instead of putting all of the stuff in parameters, let's first put it in a JOT token and sign it with a private key held by the client, all right? Second thing that changes, we put that JOT in the URL, so we send it to the STS in step 5 and 6 in this case, and that's essentially how we do that in practice, all right? And that's JSON Web Token secured authorization requests. All right, so we have the full configuration of the flow inside the JSON Web Token, which is now integrity protected. There's authenticity, and the STS will verify all of that before accepting this flow configuration. What does it look like in the URI, the authorization request? Well, the authorization request now contains 2 parameters. We have the client ID, which always has to be there. That's an OAuth thing. The spec says this is mandatory, so it must be there. And then we have a second parameter, the request. And what we see in that request is a JSON Web Token. It's in reality a little bit longer than what I have on the slides, but of course PowerPoint with limited space, I had to add like some dots in between to skip most of the contents. And that's essentially how this is going to work, and that's how we protect the integrity of these parameters. What's inside that token? Well, in that token, it's going to be a very long token. In that token, we have a bunch of claims. We have a header with an algorithm and a type, and we have the decoded payload. The payload is the body of the JOT, and you can see that in that body we now have the flow configuration parameters. We also have some additional parameters like the issuer and the audience, which are JOT-specific claims. The issuer is, of course, who created the token, which would be the client. That's the client ID. And the audience is who is supposed to consume the token, and that would be our authorization server, in this case, sts.restofit.com. All right? Other than that, we have flow configuration parameters. There's a requirement that the client ID in the JOT matches the client ID in the URL, which is kind of obvious, but it's a check that STS must do. And then, of course, the other stuff is the normal flow configuration. Everything that you would normally put in request parameters, you now drop into that JSON Web Token. And that's essentially how this means. The spec defines an explicit type for the JOT. This is a JSON Web Token best practice of using explicit typing. This is now adopted by all new specs, so you can see that this is now a very specific type and purpose of that JSON Web Token. The key ID is used by the STS to identify which key the client has used for verifying the signature, and that's essentially how JOT-secured authorization requests work in practice. All right? I have a demo for that. Before we dive into the demo, I want to make sure that your expectations are accurate. The demo is extremely underwhelming, as in it's not going to be exciting. It's not going to be like, oh my God, that was the best demo ever. It's really not, so that's one thing. The application doesn't do anything, that's the second thing. And we're really concerned about the authorization requests and, of course, how we can implement that on a client. So with your expectations set like really low, we can now dive into the demo and take a look at what's happening. What do we have here? I have a sample application here about securing authorization requests, and we can click the button to start. You can't see this? Thank you for letting me know, otherwise that would be screen mirroring. Is this the right one? I have no idea. Probably not. Okay, let's just do it like this then. Now you can see it, all right? I'll just have to focus on that screen because it's no longer here. So what we have here is, yes, thank you. What we have here is a client application, right? It's a backend web application, just in the slides. It's a confidential OAuth client, and we can start an authorization code flow. And if you click this button, it will basically run a flow against our security token service, which is an instance of identity server, because it does support all of these features. So we can log in with the user, and my username is Bob, and my password is not Bob, trust me. And we can log in, and we come back to the client application. All right. I also have no internet, that's going to be interesting, but everything should be fine. Like I said, underwhelming demo, even with failing CSS. But what is the interesting part is basically what we have here, right? In the network tools right here, we have the authorization request with all of the parameters. That's a normal authorization code flow. You can see right here we have a client ID. Let me highlight this. We have a client ID, we have the scopes, we have the code challenge, and all of that stuff is included right there. Normal authorization code flow as you've run this plenty of times. Good. What else, or what are we going to do next? We're going to update the application. So you can't see this either, I know. Let's move it here. So I've implemented this in Node.js. I was running the authorization code flow, so we're going to comment this line and uncomment this line. So I promised you an underwhelming demo, here we go. So that's all there is to it. What do we do here? I'm going to show you that. We're basically using a library to handle this. So I'm using an OIDC library for JavaScript, and this library has support for generating JSON Web Tokens and sending requests. So what we're doing in line 107 is basically creating that JSON Web Token. It's going to be signed with a private key that we have configured this client library with, and we include that request object in the URL right here. So in the URL, we include a client ID, as you can see here, and we include a request object, as you can see here. We're constructing this manually because the library adds like a whole bunch of other parameters which aren't really supposed to be there, but it's a thing that the library does. So we're doing this manually to show you what it's supposed to look like in practice. All right. How do we configure this library? It's going to be on top. On top here, we basically set up this library to use a private key. So we read a private key that is stored in the code repository right here, which is, again, not a best practice, but you kind of understand how this is supposed to work. You get the private key from your secrets management solution, you load it in the library, and it should be good to go. Why does this work? Because the STS is configured with a client public key. Let me grab the window and show it right here. This is identity server. It is configured with a client. This is the client ID here, Node.js, and the client has a public key that is configured with the STS, and that is the public key that the STS will use to verify the JSON Web Token. That's why this works in practice. All right, let me show you the effects. If we go back to our demo right here, we clear this, and we run this again. We are, of course, still authenticated, so we don't have to log in as Bob with our super secure password again. But what we see here is basically jar in action. We have the client ID, as I showed you in the slides, and we have a request object, and this is the JSON Web Token with all of the parameters that we had before. That's essentially how jar works in practice. All right? As I said, it's some minor modifications to the authorization code flow, but it adds a lot of security to that authorization request. Good. Brings us to a takeaway. Use jar. Jar is a JOT-secured authorization request. It increases the security of the request. The takeaway here is like, yeah, jar is really awesome and so on. In full disclosure, the next topic is another way to secure the authorization request. It's actually better. So you can kind of forget about jar. It's useful, might be useful for you, but the next one is going to be better and a better practice. All right, so let's dive into PAR, because why not, right? The R is the authorization request, so we have jar and PAR and so on and so on. PAR is pushed authorization requests, all right? This jargon, by the way, is absolutely awesome if you want to sound like really smart or really crazy. Just start talking about jar and PAR and DPoP and so on, and everybody's like, what the hell are you talking about? Pushed authorization requests. PAR. What does that do? PAR changes the way the flow works. And it's actually really, really, really awesome. All right, so pay attention, because this is really important. We still start a flow with the client initiating like, hey, we want to run an OAuth flow, whatever. And then the user does. Then the client is like, okay, we're going to start a flow. And it creates like the flow configuration, which we previously put in a JSON Web Token, and now we're going to send that to the security token service. We're going to do a server-to-server call and be like, hey, man, we're going to run a flow with this configuration. What do you think about that? And the STS will evaluate that, will verify that request, and be like, yeah, that seems like a solid config. And it will store that and give you an identifier. All right? And that identifier is what the client uses to run an OAuth flow. So now it starts the flow. It's like, yeah, go to the STS with an ID, and that's it. No flow configuration, just an identifier. The browser follows that request, goes to the STS. The STS is like, aha, a PAR ID. It's going to look up, what does that mean? Like, oh, yeah, that's this flow, of course. Makes sense. Handles the authorization code flow just like before, user authentication with my more secure password than the one from Bob, and off we go. And we get an authorization code. This is a normal authorization code flow, by the way. We get the authorization code, we exchange it for tokens in step 11 and 12, and we can access our APIs and so on and so on. This is basically what PAR brings to the table. And it completely changes the properties of running an authorization code flow, and it makes things increasingly better. Like, there's a lot of benefits here. First of all, imagine that the flow config in step 2 is invalid, that you're using like wrong parameters or a wrong URI or I don't know what. Then the STS will be like, that's not a valid flow. And we don't have to show like this ugly error page to the user like, oh yeah, something went wrong, we don't know what. We can actually abort the flow before it even started. That's a good thing. That's essentially it. And we no longer have that information in the URL. It's invisible even to the front channel. No more decoding JOTs to see what's in there. There's nothing there. That's another benefit. And the third benefit is that JOT can be like really long and you're pushing it into a URL parameter, which means it has to be transferred. Now there's nothing there except the identifier, so the URL becomes a lot shorter. That's PAR in a nutshell. All right, what does it look like behind the scenes? You can already expect a super exciting demo coming up. But for now, let's actually show you some relevant details. There's a PAR request. So there's a new endpoint on the STS supporting PAR, and that endpoint accepts a flow configuration just like we've seen before. This is the exact configuration you would normally cram into URL parameters. You now send it to the STS in step number 2. All right? That's essentially what this means in practice. This is an authenticated request. All right? So the client has to authenticate to initiate PAR, meaning that it's only available for confidential clients, but that's essentially a very useful case in this instance. Good. Once we've done that, we have received a PAR ID. Here's the response from the STS, step number 4. We get a request URI, which is basically a URN, uniform resource name, which contains the actual PAR ID at the end. And we have an expiration time and so on, and off we go. Good. What do we do with that? We start the flow. We include a client ID, because like I said earlier, OAuth says there has to be a client ID, so we include it. And then we include that request URI parameter, which contains our PAR ID, and off we go. That's all the information there's available. There's nothing left to tamper with. There's nothing left to inspect. It's just a random identifier that only means something to the STS. And that's how the STS will find the right flow configuration and handle PAR in practice. All right? Let's take a look at the demo. I think I've set your expectations low enough here, so we're going to go here and comment. If I find my mouse, here we go. We are going to comment, I missed it here, this line, and uncomment this line. All right, what does this do? Actually, it uses the library to handle this. So the library supports push authorization requests. That's how you want to implement this. You really don't want to do this by hand. You can if you have to. It's not that complicated. But ideally, you can just tell the library, like, yeah, go do PAR for me, and it will handle the request. It will give you the response, which we nicely print out, and then we start the flow with that request URI parameter. All right? Let me also show you my pretty terminal so we can actually see what it's printing out. There we go. Let's make this a bit bigger. To our client application. We clear our network logs. We reload this. To be sure, you click the button, and it will now run a flow. And in this flow, we now have a request URI. All right? And this is the PAR ID. It's like a very long random identifier, means nothing to us, but it works because here's the response with the authorization code, and so on and so on. All right? The reason I showed you this is because here there's a bit more information. The PAR request is handled by the library, so it's hard for us to print it out. We don't see it, but the request is going out behind the scenes. And here's the response from the STS with the request URI, with a PAR ID, and there's an expiration time as well, which I can't see because, oh, yeah, that's why. There we go. There's an expiration time here as well, which in this case is 10 minutes. And then, of course, we send the browser with the PAR ID to this, and we get the tokens in response, and so on and so on. And that is PAR in action. All right. If you're using PAR, awesome. There's a second thing. If you're using PAR for a client, you probably want to configure, or you should configure that client as PAR only. And an STS will support that. So typically in an STS, you can say like, hey, this client can only send PAR-based requests. And that turns off the normal authorization code flow. So it also avoids someone from trying to do like a PAR downgrade attack or something like that. We can basically configure the STS like PAR or nothing for this client. And that means once you do that, then every client will start using PAR. PAR is absolutely awesome, right? The security properties from PAR are really good. And it's kind of so awesome that it has people wondering like, why didn't we do this in the first place? Like, what's wrong with us? Why didn't we think of this 10 years ago? That would have been awesome if we had PAR from the beginning. And that's essentially how awesome PAR really is. And that's essentially why you want to start using PAR today if you can, all right? It is very likely that PAR will become the default in the next coming months or years. PAR will become the best practice for running authorization code flows with confidential clients. It's that good, it's that awesome, all right? If you use PAR, then jar is probably not very useful, all right? There might be some cases where you're not really exactly sure that the PAR request is safe because there might be middle boxes inspecting traffic in between and so on. In that case, you might want to add a signature to the data with jar, but it's very likely overkill for your particular use case, all right? And that wraps up securing the authorization requests. Breathe. We have 25 minutes left. All right. One more topic. I'm going to need all the time, by the way. So if you're like, oh yeah, we're already done, that would not be true. We have one more very important topic to talk about, and that is sender constraint tokens. Sender constraint tokens are one of these things that have been a goal for a very long time, right? So what is this all about? This is about the access token. This is about the final step in this picture, step number 10, where we access APIs with access tokens. So a lot of security focuses on step 1 till 9, right? And all of the stuff we talked about focused on that. Resource indicators is the first step for limiting the power of 10, but we still have bearer tokens in practice, all right? Bearer tokens meaning that the holder of the token automatically gets the authority to use the token. Bearer is the name for that. Bearer bonds is the same thing. Like if you have bonds on paper, if you can steal them, then now they're yours. There's no authentication, no nothing. It's once you have it, you can use it, all right? And that's kind of a very unfortunate problem to have. And it's a problem that people have been trying to solve for a long time. Even from back in 2012 when OAuth 2 was released, they're like, yeah, we probably want to lock this down in like a following spec. And what really happened is that people tried really hard and never succeeded. And there's been attempts at getting rid of bearer tokens with a better mechanism, and they never went anywhere. And we had like a brief period with token binding in browsers. I don't know if you remember that. And a lot of people were super excited, and then browsers killed it like, yeah, haha, we're not going to do that for some privacy reasons and so on. And that left us with bearer tokens for a long time, so long that they've become the de facto default type of token. And a lot of people don't really move on to something else, even though we have options today to get rid of bearer tokens. And that's going to be my final topic. It's a very long topic, but the final one I'm going to discuss in detail. All right? What we're going to do is we're going to transform our bearer tokens into sender constraint tokens. That's the official lingo for that type of token. It basically means, translated, that you have to prove possession of a secret while you're using that particular token. And for access tokens, that's going to mean that we have a proof of possession mechanism where we typically prove that we possess a private key. All right? We prove that we possess a particular private key, and with that key, we can sign something proving that we possess it, and that allows us to use this particular access token. That's in a nutshell how this is going to work. Now, we've had a whole bunch of proposals for this that not really took off. And today, we actually have two options. There's two reliable options we can use to implement to implement sender constraint tokens. My apologies. Option 1 is the use of TLS, MTLS to be specific, and option 2 is DPoP, demonstration of proof of possession. Another abbreviation, very catchy, DPoP, sounds really cool. It is actually pretty cool, and we're going to talk about both mechanisms in a little bit more detail. MTLS has been around the longest. MTLS is basically where the client uses a client certificate to set up an authenticated TLS connection with a remote party, the STS and the API concretely. And because they can set up the connection, they have proven they possess the private key that belongs to their certificate, and the access token is going to be linked to that certificate, and the whole picture makes sense because that's how we get sender constraint tokens. So how does this work? We have the client, we have our STS, and we have our API. And the client has a private key, the corresponding public key, and the certificate and the public key, which are typically linked together, and so on and so on. And the STS is also configured with the client certificate. So this is not a blindly certificate that we have to verify trust from. We know it up front, right? The client is configured like, hey, this is going to be the client certificate, or one of them, and the client will use that certificate to authenticate while proving they possess the private key. Good. This means that this works with self-signed certs, so you don't have to go out and get one from an actual CA, which saves you money or hassle or whatever. You can use your own certs for making that happen. So how does this work? The client is going to set up an MTLS connection. That's like the nice cylinder. You can see I'm a PowerPoint wizard for drawing these things. But basically that means this is a secure connection with MTLS that the client has proved that they possess the secret that belongs to their certificate. That is now a secure connection. Over that connection, the client can exchange an authorization code or a refresh token for new tokens. All right? That's how this works. What the STS does to make sender constraint tokens is it will actually bind that token to the certificate by including the fingerprint of the cert into the token, making this a sender constraint token, and it will give the client their tokens. What does the client do? The client now wants to call an API, so it uses MTLS to contact the API. The API doesn't really verify the client certificate, it's just like, yeah, here's a cert, fine by me. And then the next step that will happen is that the API will process the access token. It will see that this is a sender constraint token, and it will basically verify that the certificate embedded in the token is the same certificate used to set up the TLS connection. If it is, then the client has already proven that they possess the private key that belongs to this certificate through the TLS handshake. So everything is handled on the TLS layer, no application implementation, fairly straightforward to get this working in practice. All right, and that's how MTLS works behind the scenes. Inside the access token, if it's a JOT, or in the claims, if it's a reference token, you will now find a new claim called a CNF claim, which means confirmation. And in the CNF claim, you'll find an X5T S256 claim, which basically means this is an X509 thumbprint, like a fingerprint of the cert, using a SHA-256 hashing function. Just an implementation detail, but that's what happens behind the scenes. So the API sees a token like this, sees a CNF claim, it's like, aha, sender constraint token, it will verify that the certificate is actually correct, and so on, and only then accept the token. That means if the attacker ever steals this, they can try to contact the API, but they can't succeed in setting up that MTLS connection without the private key of the client. So we're kind of assuming they can't steal private keys, otherwise the whole thing just falls down, because that is kind of the requirement to make this work. All right? And that's essentially how we make sender constraint tokens. Only the holder of that private key is now able to use this particular token. Good, easy, awesome. MTLS, I don't have a demo for this, but if I had a demo, it would be extremely underwhelming as well, because you basically configure a TLS library with a client cert, and everything else happens automatically, right? Everything else happens because the MTLS library does the handshake and so on, so we don't really have to implement anything. It's just the API has some small bit of additional logic to accept these tokens, but that's about it. If this is so awesome, why doesn't everybody use it? Because, well, MTLS is not always practical. Sometimes you have like middle boxes in between. An API gateway would terminate the TLS connection, so now you have to start forwarding like cert information to the actual API. It can get pretty messy, and sometimes you don't have control over the client enough to use MTLS and so on. It can be a bit messy to deal with in practice. And that's why we also have an application level mechanism called DPoP. And DPoP is demonstration of proof of possession. It's basically the same mechanism, but instead of everything happening automatically, you now get to have the joy of doing everything yourself in the application code. All right, well, you want to use a library for that, but in essence, it's very heavy to implement, but once you get there, it gives you the same properties in practice. It is really awesome because the application level feature gives us a lot of flexibility, makes it a lot easier to handle this in a whole variety of cases, and DPoP is actually really, really useful and really popular in practice as well. How does it work? I'm going to walk through the concept first, and then we'll zoom in on the different steps. All right? Conceptually, the client has a key pair, a private key and a public key. In this example, the key pair is ephemeral, meaning that the client can just generate it on the fly. It doesn't have to be pre-registered with the STS, because this also works for public clients, not just for confidential clients, also for public clients. All right? So you can perfectly fine use this in a mobile app, for example. That would work really well in practice. What do we do then? We run our authorization code flow, and we exchange our code for tokens. And when we want to exchange the code for tokens in step 3, what we first do is we generate a DPoP proof. Right? DPoP proofs are JSON web tokens, and they serve as a function to say to the STS, like, hey man, we actually possess a private key. Here's a signed JOT to prove that we have a private key for this particular public key. All right, so we generate that DPoP proof, and we send it along with the authorization code or the refresh token to exchange that for new tokens. And the STS will verify that. STS will be like, hold on, I'm going to make sure that what you give me here is indeed a JOT with a valid signature and so on to see that you actually have the private key belonging to this particular public key. All right? If that's the case, the STS will give you sender constraint tokens. It will basically embed the public key inside the access token and give you that access token. All right, that's now a sender constraint token, meaning that we have to prove possession of that private key when we use that against an API. So we want to call an API, what do? Same thing, we generate a DPoP proof in step number 7. We sign that proof with our private key and include it along with our access token on the actual request. All right, off we go. What does the API do? The API is like, hold on. This is a sender constraint token. I'm going to verify that. And the API will do like a whole bunch of verification steps. If you actually read the spec, there's like 12 or 13 things you have to check for, so there's a lot of burden on the API here to make sure that this is actually correct. And if everything checks out, everybody happy, we get a response, and off we go. That's how DPoP is supposed to work. All right? DPoP ensures that only the client with a private key can use this particular access token. And the spec has gone through a couple of iterations to ensure that it covered all of the weird attack vectors and corner cases and so on. And it's actually a really solid spec, which is well designed, well written, and very clear for implementers as well. All right. All good? Let's zoom in on some of the details. Detail number 1 we're going to talk about is step number 2, the DPoP proof that we generate to call the STS. All right? So that DPoP proof looks as follows. Like I said earlier, we have explicit typing for new specs using JOT, so DPoP plus JWT indicates this is a DPoP proof in the format of a JSON Web Token. The client includes their public key with this. This is the way we send our public key to the STS, so it can bind the token to this public key. We send it along as part of the signed data. In the body, we find a GTI, which is a JSON Web Token identifier, a unique ID for a JOT, that will be used by the STS to do a replay prevention. So it will keep a cache of previously seen GTIs, and it will reject anything it has seen before. All right? We also include the endpoint we're calling and the HTTP method in line 11 and 12. We basically say this is a post request to the token endpoint. All right? That limits the power of the proof. It's only valid for one specific endpoint in practice. And then we include an issued at timestamp, allowing the STS to verify when this token was issued, or this proof was issued. And that allows the STS to enforce freshness. Like the STS can be like, I only want DPoP proofs from the last minute. I don't want anything older, because why would I accept old stuff? That makes no sense to do that in practice. And that is the proof that we include in step number 3. And this JOT is signed by the client's private key, and that will be verified by the STS. All right. How do we send it then in step number 3? Well, we include this in a new header called DPoP. So there's a new HTTP header, DPoP, which is designated to hold DPoP proofs. So that's how we get that proof to the STS in practice. All right, everything else here is still the same. It's an authorization code exchange for tokens, so it's basically a request to the token endpoint, as we've done so many times in an authorization code flow. Good. The STS will verify this. Why? To ensure that the client actually possesses the private key, to ensure this is not like an attacker using another proof or something. The client has to sign this JOT, make sure it's actually relevant or valid, and so on and so on. Good. Step number 5, binding the token to the key. How does that work? Well, we already saw this for TLS. It's kind of the same thing here. We add a CNF claim, but instead of doing like an X509 certificate thumbprint, we now do a GKT, which is a JSON Web Key thumbprint. All right, so this is basically the thumbprint of a key represented in a JSON format, and that is embedded in the access token. That's how the API will recognize this as a sender constraint token as well. All right? Good. Self-contained access token, of course, also works with token introspection and so on. Good. We get those tokens to the API, to the client. Not very interesting, so nothing to see there. Normal token response with an access token, potentially a refresh token, an identity token, whatever. On to calling the API. What do we do next? If we want to call the API in step 7, we generate a new DPoP proof. And that DPoP proof looks very similar to the one we used or generated in step 2, but there's a few changes. First of all, the most important change is going to be the HTTP method and URL in line 11 and 12 are now for the API. So this proof is limited to one specific API endpoint for one specific HTTP method. All right? That's very important. Again, we have a unique identifier to handle replay protection and so on. Line 14 is also new. 14 is the ATH claim, which stands for access token hash. All right? So if you're proficient in this, after a while, you know what all of the three-letter abbreviations really mean in practice. Access token hash, and this uniquely links this proof to this particular access token. So an attacker can't take like a proof from one request and then just attach it to another request, because that might work, but that shouldn't work. And this means that the proofs are linked to access tokens explicitly. All right, and all of that is signed by the client's private key. All right, brings us to step 8. How do we get that DPoP proof to the API? Well, there's a header for that. Of course, we include the DPoP header, and the DPoP header contains the DPoP proof. There's one additional change here. This is a normal API request with an authorization header. What did it say before? Authorization bearer something something with a token. Now that changes to DPoP. Line 3 shows you the authorization header. It's no longer a bearer token, but it's a DPoP token, a sender constraint token. And that's a way to inform the API that this is supposed to be a DPoP-based token, and the API will check all of the necessary things in practice. All right? What does the API check? Well, to be honest, if you need to implement this, please read the spec. The spec is very clear. It has like a very clear list of things the API must check, and there's a whole bunch of things, a lot more than I can put on the slides. But in a nutshell, this is a summary. In a nutshell, the API will verify the signature on the JOT proof. It will ensure that the payload corresponds to the actual API call, like that it's the right endpoint and the right method. And it will ensure that the access token is in the request is correctly linked to the DPoP proof and so on. And of course that the public key in the token matches the key from the public key embedded in the proof. All of these things have to be checked by the API. And that basically gives us sender constraint access token on the application level. All of this is implementable in code. It requires no configuration upfront. All you need is support from the STS to give out DPoP tokens, and you can do everything from the client side now, from the client's implementation, which is very, very useful in a lot of specific use cases. All right? One more thing. If you're building an API, you must have a check in place that actively rejects any bearer token with a CNF claim. This is very important, otherwise the attacker could take like a sender constraint token and just throw it in an authorization header with like type bear, and the API is like, yeah, good enough for me, bam. And that would of course kind of make this whole discussion very useless and circumvent all of the protections here. So the API must have a check. If it's a bearer token and there's a CNF claim, like no, go away. 400 bad client or 403 unauthorized or 500 internal server error if you like to have like one error message for everything. 500 is perfect for that. So whatever you want, as long as you reject it, I'm happy. All right? Brings us to the takeaway here. Sender constraint tokens are really, really useful. The days of bearer tokens should be over. Sensitive applications should absolutely start using sender constraint tokens. It's something that you want to start working with in practice, get your hands dirty, learn how it works, so you can learn how to adopt this in your specific applications as well. All right? And combined with all of that, we have really solid security. All right, so this was a very wild ride. A lot of OAuth security in 53 minutes, so that's probably a new record. So I hope you kind of grasped all of that. I hope you still have some cycles left to carry this takeaway. Takeaways here. If you're building confidential OAuth clients, you can really supercharge security. There's a lot of things you can do. PAR should be the default for your authorization code flows. All right, so if your STS supports this, if you can use this, start using PAR. It's really, really awesome in practice. And then we should think about sender constraint tokens, both for confidential and for public clients. It's a really good idea to do that. It's not as simple as I'm making you believe on PowerPoint slides. There is going to be some key handling and so on in practice. You'll have to learn how to work with this. I know it's not always that easy, but it's something worth putting in the effort to try and get this under control. MTLS and DPoP are very stable. They're here to stay, and you can use them in practice. This is not going to be a wasted effort. All right? With that, I want to thank you very much for being here. I hope you enjoy the rest of the conference. If you have any questions, we're not going to do live questions. That's not going to work well with the lights, but you can come up here and talk to me after the session. That would be perfect as well. Thank you very much.